everyone, I am Juhi Gaur from Department of Computer Engineering, Silver Rock University. The subject is data structure and this video is about remaining topic of unit number 5, searching and sorting. So in this video, we are going to learn about the remaining sorting techniques, which are quick sort and merge sort. Now let's just study about the quick sort. Quick sort is a highly efficient algorithm where it is sorting element based on partition of array of data into the smaller arrays. That means quick sort is basically using divide and conquer method, and that is why we can say that quick sort is divide and conquer algorithm. At each and every step of the method, the goal is that we have to place a particular record into its final position with the table. In doing so, all the records which precedes this particular records will have the smaller key, while all records that follows the largest key will be going to at the upper part. So we can say that this particular record is termed as pivot element. The same process can then be applied for each and every sub tables and will be going to repeat it until and unless we are having each and every records at its particular position. So basically there are different version of quick sort that can pick the pivot element in different way. So in our case we have considered the version where we are picking up the very first element as pivot. What we can do is we can pick the first element as pivot. We can also have the various other version where we can pick up the last element as pivot. Otherwise, we can pick up the random element as pivot, or we can also take the middle one as pivot, whatever we would like to implement. So we have to choose one version where we can decide that which will be our pivot. Quick sort partitions particular array and then call itself recursively until and unless it's being sorted. So we can say whenever first time it will be call itself, it will be divided into two sub arrays. We can say that this algorithm is quite efficient for larger size of data sets. So we can say that the average or worst case complexity of this algorithm is big O of n square, where this n is particularly defining number of items in array. So now we are going to sort this array using quick sort. So we have considered the first element as pivot element, and that is why our lower bound will be first index and upper bound will be the last index. We need to find out our proper position of pivot in the sorted element to perform the operation, and then we are repeatedly do this thing for each and every sub array of it. So for now what we have done is we have selected our very first pivot, which is our first element, and lower bound is same, first position, and upper bound is what? Last position. So here we can see the algorithm as well as the example of quick sort. So for quick sort, first of all, we will set flag is equal to true. Now we will check that if lower bound is less than upper bound, then we will set I is equal to lower bound, and we will set value of j is equal to upper bound plus 1. As well as we are going to set the key, and key will be k of LB, which is the lower bound key value. So now we will increment I by 1 and we are going to repeat this incrementation till the flag will be true. As well as we will increase I by 1 and decrement j by 1 till k of I will be less than k. We will decrement j by 1 till k of j is greater than k. Now, if I will be less than j, then we are going to swap value of k of I and k of j. Otherwise, we will going to set the flag at the false. So at the end, we are going to swap value of lower bound and value of j. So we can say we will swap k of LB and k of j. We will better understand by the example. So now let's see the example. So here is the case that we have the value of I is equal to j. So we can say the value at I is equal to 0 is 42. And now what we are going to do is we are going to increment the value of I by 1. So now I is equal to 1 and at that time the value at I is equal to 1 is 23. Now what we are going to do is we will decrement the value of j by 1. So previously the value of j was upper bound plus 1. So now it will be at the upper bound. As well as we are going to increment value of I by 1. So now I is equal to 2 and the value is 36. Our j was at upper bound, so we are repeatedly decreasing the value of j until we find the value which is greater than particular value. So we are not finding any kind of value where we can say I is less than j. So we are finding it where we can say that we are finding this particular thing at the I is equal to 4. So as of now what we have done is we have just decremented and incremented value. We have checked up that whether the value of I is less. If it is less, then we are keeping it as it is. So we can see that the value of I is equal to 3 is what? 42. In the next step, because we have swapped up the value with 11 as of 11 is less than 42. So we have swapped those two values. So here I is equal to 0 and we can say lower bound is set as 0 and value of I is also 0. So at 0 we have the value 11. If we talk about j, then j is equal to 3. Index of j is 3 and at that time the value is 42. What we are going to do is we are going to increment the lower bound. So now the lower bound is where? Lower bound is 1. So value of I will be 1 and we are going to decrement upper bound. So upper bound is at the index 2. So if we look at the half portion of an array, left hand side of array, we can find out that we are having the shorted elements. 11, then 23, then 36 and then 42. So we have all those elements shorted. As of the previous portion was shorted, now we can move forward for the right hand side of the array. So now what we can do is we can set our lower bound at the right hand side. So our lower bound is at the index 4 and the upper bound is where? At the index 9. So now what we can do is we can check the index number 4 and index 5. If we check this two value, we can find out that 65 is greater than 58. As of 65 is greater than 58, we can swap off these two values. So we are swapping off 58 and 65. After swapping, we have found out that we are having this two shorted array where we are incrementing value of LB and decrementing value of UB, which is upper bound. As of we are doing so, we are having the second portion where we are having the shorted element. So now 58 and 65 is its right position. Now we are moving ahead, we are incrementing the value of lower bound. So now the lower bound is set at index 6 where the value is 94 and upper bound is the last element. Now we are moving ahead. Now as of we are comparing the next portion, we can find out that 87 was at the end of the array. As of we are comparing this content with the previous one, 99 is greater than 87. So what we can do is we can swap these two values. So now 87 is located at the second last index and 99 is located at the last index. Now we are moving ahead and what we are doing is we are comparing the lower bound's value with the second last element. The second last element is 87, which is smaller than the lower bound, which is having the value 94. As of 94 is greater than 87, the values will be swapped. So now we are having 87 at the fourth last index and 94 at the second last index. As of we are done with it, now what we are going to do is we are going to compare 87 with 72. As of we can find out that 72 is less than 87, we can swap these two values. As of we have swapped these two values, now obviously our lower bound is as it is and our upper bound has been decreased. Based on that, now we can find out that we have the shorted array. So this is how we can short our unshorted array using quick sort, using our quick sort algorithm. So whatever we have done in previous example has been described over here in the form of algorithm. So what we can do is we can call the quick sort algorithm recursively for each and every iteration wherever the lower bound starting where it is located and upper bound will be j minus 1. Similarly, we can call the quick sort algorithm recursively for each iteration where the lower bound is starting with the j plus 1 and upper bound starting where it is located. Same thing will be happen with the third iteration, third recursive call we can say, where the lower bound is starting where it is located and upper bound will be j minus 1. So we can do these things unless and until our unshorted array will be shorted. Now we will learn about the merge sort. So we can say that the operation of sorting is closely related to process of merging. Merge sort is basically divide and conquer algorithm, because it is based on the idea of breaking down a list into various sublists until and unless we can have the single elements. It will going to be divided into sublists until and unless we are going to have the single elements. Now we are going to merge this up So merge those sub lists in a manner that it can be result in the sorted list. So what will be the procedure? First of all, we are dividing unsorted list into n sublist, each containing how many elements? As we have discussed, one element. Take the adjacent pair of two single lists and merge them to form list of two elements. N will be now converted into n divided by 2 list with the size of 2. We are going to repeat this process till a single sorted element will be obtained. So by this process we can say that the time complexity of merge sort will be big O of n into log n. As of we are dividing it into single elements, and after that we are merging up those elements until and unless we are having the sorted array. That is why the time complexity will be big O of n into log n. So here we have the example of merge sort. So as of we can see that we have the unsorted array where we are having the 8 elements starting from this index 0 to 7. To divide this particular array into two parts, what we can do is we can do the summation of first index and last index, and we can divide it by 2. So we have 0 plus 7 divided by 2, we can find out value 3. So what we are going to do is 0 to 3 will be my one portion, left hand side of portion, and 4 to remaining 7 will be my second portion, and its index will going to change. The index 4 will become 0 and index 7 will become 3 as of it has been divided into two parts, and this will be going to work as the individual array. So here we have two portions, or we can say two sub arrays, left hand side and right hand side. So what we are going to do is we are going to again divide this elements, or we can say sub array, until and unless we will find a single element in an array list. So starting from the left hand side, what we are doing is we are dividing 724, 521, 2 and 98 into two different portions. After that, similar thing is happening with two elements array. We are dividing this elements into single list of array. So we are having 724 as an individual sub array, 521, 2 and 98. These are our individual sub arrays. Now what we are going to do is we are going to start merging these elements. We are going to merge up the single elements into one array, and as well as we are comparing these elements, that if another element is less than another left hand side of element, then what we are going to do is we are going to swap these values. Like 724 is basically greater than 521. So we are going to swap these two values and we are going to form a single array for these two elements, 521 and 724. Same thing will be going to happen for the 2 and 98. If we compare this two, 2 is already less than 98. So both will be not going to swapped up and both will be at its right place. Now we are going to merge up these two sub arrays and we are going to form 4 elements array. So as of we are doing so, we are going to again compare these elements with each other, and we are going to find out that which are the smaller element. We are keeping it in ascending order. So we are going to form one array where we are having values 2, 98, 521 and 724. So this thing has been happened for the left hand side of array. Now we are starting with the right hand side of array. Right hand side of array starting with 529, 31, 189 and 451. Similar thing we are doing for this stuff, that we are dividing into sub array until and unless we are having the single element in array. So at the end we are having 529, 31, 189 and 451 as an individual sub array. So again we are going to merge this up like we have done in left hand side of sub array. So we are comparing 529 with 31. 31 is less than 529, so we are going to swap these two values. Now we are going to compare 189 with 451. As of we can say that there will be no change or no swap over here, as of both are at the correct place. Now we are going to merge up these two sub arrays, 31, 529, 189 and 451. As of we compare these two arrays, we can have one single array where we are having this 4 element together. And the sequence will be 31, 189, 451 and 529. So we can say that left hand side and right hand side of sub array are already being sorted. So now we are going to merge these arrays into the single array. Both will be the sub arrays. Now we are going to form this up into the single array. And again we are going to compare each and every values until and unless we are having the sorted elements. So as we can see that at the end we are having the sorted sub array. 2, 31, 98, 189, 451, 521, 529 and 724. So this was about the merge sort. We have seen the example as well as algorithm of merge sort. I hope you understand it well. Here we have our very last sorting technique, which is insertion sort. So now we will discuss insertion sort. So in insertion sort, each and every iteration moves an element from unsorted portion to the sorted portion until and unless all the elements are sorted in our list. So let's just see the insertion sort. So first of all, let's just assume that first element in the list is in the sorted portion of the list. So what we can do is remaining all the element will be in the unsorted portion. Now what we can do is in the second step, first of all we will see the very first element from the unsorted list and we will insert this stuff into the sorted array. And we are going to see the order of it. We have to organize it in the order, specific order. So now let's just repeat this particular process until and unless each and every element from the unsorted list will move into the sorted list. We can say that this is the easy one, but we cannot apply this algorithm for the larger data set. So we have to take care of that this can be applied for the shorter data only. So here we have defined the complexity of insertion sort algorithm. So we can say that if we wanted to sort the element with the n number of element in unsorted list, then what we need is we need comparison of n into n minus 1 divided by two numbers. So we can say that if the list is already sorted, then we need the comparison of n numbers. That is why we can say that the complexity of insertion sort in the worst case is theta of n square. Similarly, the time complexity in best case will be omega of n. And in the average case, it will be theta of n square. So let's just understand the insertion sort with an example. Here we have the unsorted array which is having various elements in it. Now first of all what we are going to do is we can take first number is 6 and we are considering that this number is sorted. Now what we are going to do is we are having the second sub array where each and every element are unsorted. So we are start inserting this unsorted elements into the sorted array, as well as we are going to compare this unsorted elements with the sorted array. If unsorted array is less than the sorted one, then we can organize it in the proper place. So first of all, we can say that we have the unsorted element 5. We can compare it with the sorted element 6. So we can find out that 5 is basically less than 6. So we can swap these two values up. So now we are going to have what? 5, 6, 3, 1, 8, 7, 2, 4. Now we will consider that 5 and 6 are in the sorted sub-array, and we are going to consider each and every element on words second index as an unsorted array. And we are going to repeat this procedure until and unless we will find out the sorted array. Now we are going to select the third record and we are going to insert this record in the proper position. So if we compare 3 with 5 and 6, we can find out that 3 will be basically at the 0th index, 5 will be at the first index, and 6 will be at the last index. So we are going to sort this up in that particular manner. Now we are going to consider that 3, 5, 6 are sorted subarray and 1, 8, 7, 2, 4 are sorted and unsorted elements array. So now we are going to select the fourth record and we are going to insert this in the sorted array. As of we are comparing it, we can find out that 6 is basically greater than 1. So we are going to swap this up. Similarly, we can find out that 6 is greater than 5. So we are going to put 5 in the second index. Similarly, we can find out that 1 is basically less than 3, 5 and 6. So we are going to put 1 in the first index and other element in the sorted manner. So we can have the sorted sub-array 1, 3, 5, 6. As well as we are going to consider that 8, 7, 2, 4 is unsorted. We are going to repeat this process again. As of we are repeating it, we can select the fifth record, which is 8. We are going to insert this into the proper place of the sorted array. So we can say that it is already in the proper position. We are not going to swap this value with anyone. So we are having 1 to 8 in the proper sorted array. 7 to 4 are still unsorted. So what we are going to do is we are going to select the sixth record. Sixth record is 7. We are going to insert this into the proper place. So we can find out that 8 is greater than 7. So we are going to swap this up. 7 will be at the position of 8 and 8 will be at the position of 7. So now we are just going to have two elements as an unsorted sub-array and other elements are already sorted. We are going to repeat previous stuff with the next unsorted array. So now we are selecting the seventh record, which is 2. We are repeating this thing, and what we are doing it is we are placing 2 at the proper position in the sorted array. So we are finding out that we are having one sub list of sorted array, something like this: 1, 2, 3, 5, 6, 7 and 8. Now only one unshorted element has been left. So the we can say that in the very last step we are going to select the 8th record, which is 4, and we are going to place it into the proper position. So as of we are placing this stuff in the proper position, we can find out that 8 will be at the very last position, 7 will be at the second last, 6 will be at the third last position, 5th will be at the fourth last, and this particular position will be replaced by 4. So at the end we can see that we have the shorted element 1, 2, 3, 4, 5, 6, 7 and 8. So this is how this insertion sort algorithm is working, and this was the example of insertion sort, and that's it about the sorting algorithms. I hope you understand it well and you have enjoyed it. Thank you so much.